Hello, everyone. Welcome to APS Minneapolis in March of 2024. My name is Abraham Wolcott. I am a visiting scholar for the Ideals Crest Phase 2 Center in the Department of Physics at City College of New York in the laboratory of Professor Carlos Meriles. And very, very happy to be here and thank all the organizers for APS for allowing these on-demand videos to be produced. I'm going to go ahead and minimize our floating meeting controls and get on with the show. The title for today's talk is Nitrogen Vacancy Centers as a Source of Solvated Charges Across the Diamond Water Interface. And let's get on with it. So, as we look at this material of diamond, it's got many amazing properties that are great for photonics, great for electronics. And I've got three examples of detonation diamond, high pressure, high temperature diamond, and chemical vapor deposition diamond. Now, while all of these materials are diamond and should have a large optical transparent band gap of 5.5 eV, they should all have high thermal conductivity and high electrical breakdown properties. Each one of these materials are produced in a different way. Detonation diamond is typically 5 nanometers and is of low quality and low cost. HPHT nanodiamonds are done from a top-down ball milling of macroscopic diamond and usually have more substitutional nitrogen. And then on the right-hand side, today's talk is focusing more on chemical vapor deposition diamond, and these are more expensive substrates, and we'll be focusing on those today. Let me go ahead and change this to a laser pointer, and we'll be using diamond membranes that are terminated with the 100 surface group, and let's continue. So, diamond hosts the nitrogen vacancy center, which is a quantum bit or a qubit. It typically exists in two charge states that we care about because they fluoresce, both the NV0, which is neutral, and the NV minus. When we get that additional electron highlighted on the left-hand side by our white arrow, it creates a ground state triplet. The ground state triplet includes both the 0, +1, and -1 spin states, which can be read out optically. This is possible because of a singlet state, which is a dark state. There's a non-zero probability of intersystem crossing from the triplet into the singlet, which decreases the photoluminescence of the NV. You can deterministically switch from 0 to minus to +1 by sweeping a microwave pulse. And I'll leave that to experts at APS to get into more details of nitrogen vacancy centers. For today's talk, we also want to highlight some past work in electron hole capture and memory storage. On the left-hand side, well-positioned single NVs, 10 microns inside of a diamond slab, were produced through irradiation and interrogated optically. In this particular case, it was found that both electrons and holes are readily transported through the diamond matrix and can be understood by photoionization processes. So basically, charges are being generated from NV minus into NV0 plus the generation of free electrons. The capture cross-section of both electrons and holes was found to be enormously high, and you can check that out in a paper published in 2021. On the right-hand side, at low temperatures, the hyperfine electronic structure of nitrogen vacancy centers are interrogated and are used to encode information optically. So the hyperfine structure of the NV can be readily controlled through this ionization process, but also through using specific wavelengths of light. In the bottom right quadrant, you can see pictures being embedded inside of the same plane of diamond in XY, but are encoded at different frequencies, which are accessible through the hyperfine electronic structure of the diamond itself. And that's an example that can be seen in a small cluster in the upper right-hand side. So NVs can do almost anything, and the Meriles group are experts in this field. If you wish, please visit any of the talks in the Meriles group from March 4th to March 7th. You can look at the author index and you can readily see all of the talks that are being given. And to highlight the talk of Kongju, which is going to be expanding upon this idea of having a diamond water interface with additional information about the NV center charge dynamics and spin states. But let's get on with today's talk. So these near surface NVs are in a diamond water flow cell. And on the left-hand side, this is a schematic of our microscope. On the left-hand side, you have much of the infrastructure in order to do optically detected magnetic resonance. You can control microwaves, you can control pulse laser light through your card. And then on the right-hand side, you've got a laser source with a chopper, which is then connected to electrodes and a lock-in amplifier. And so we're going to go ahead and focus on the right-hand side in the generation of photocurrent within this photoelectrochemical configuration. If we were to zoom into this area, we would then see our flow cell where we can have water entering into and going over our stack of membranes and then flowing that out. The electrodes are made out of gold and are adjacent to our membranes inside of this 3D printed chip. If we were to then zoom in on our membranes, the membranes are 3 by 3 millimeters in XY, and at their thinnest section, they are 44 microns in the Z direction. They've been irradiated with nitrogen vacancy centers to about 5 to 10 nanometers with some residual straggle. If we want to confirm that nitrogen vacancy centers are active, we can go ahead and both look at the photoluminescence emission as well as the ODMR spectrum and verify that NV centers are in fact there. We assume that we've got about 3%, around 3 ppm, while we've got about 97 ppm of substitutional nitrogen within the diamond lattice. So now, how are these experiments done? Well, we can change the voltage, the laser power, our laser wavelength, the flow rate of water, as well as the voltage waveform. On the left-hand side, we can see that we're radiating with a green laser light with an AC bias. We can notice that the overall noise of our signal is quite large when the bias is low. If we increase the bias, we end up with a better, less noisy photocurrent. And on the right-hand side, we can change from about 25 millivolts all the way up to 10 volts while holding the laser power at 140 milliwatts. You'll notice in the inset that we get a near linear increase in photocurrent, which means we are having ohmic behavior within our photo electrochemical cell. And just to recall that this is done with 18 mega ohm water, and there is no direct current pathways between the diamond and those gold electrodes. We can also change the laser power. And in this particular experiment, we are holding the voltage to 10 volts and then readily changing the incoming laser light fluence, going from 3.25 milliwatts all the way up to 190 milliwatts. If we were to then plot laser power versus photocurrent, we've got a near linear semi-quadratic behavior for these particular membranes. Now, the next thing that people would ask is, well, how can you verify that it's nitrogen vacancy centers? It could also be P1 centers or substitutional nitrogen. Then we use different laser wavelengths. We use things all the way down to 630 nanometers, but I'm highlighting photocurrent at 594, 532 nanometers, as well as 450. Once we get into the blue regime, we should have a 1 photon photoionization of both NV centers and P1 centers. If we were to collate this information together, on the x-axis, we've got our wavelength of laser light, and then on the y, we've got our photocurrent as well. And you'll notice we're going from sub-picoamp photocurrents all the way up to above 30 picoamps when we use 450 nanometer light. So there's many, many additional details that would go into this talk, but I'm going to allow my colleagues to further get into details in our diamond membrane water interface work. So in summary and future work, well, we can say that carriers are being injected and transported to electrodes. Those could be both electrons and holes. P1 centers and NV centers play additional roles with that photoionization that was highlighted in the introduction. So we've got injected carriers, which could be solvated electrons, similar to Hamer's in 2013, where he did a photo reduction of nitrogen into ammonia using solvated charges with hydrogen terminated diamond. But we could also do photocurrent detected magnetic resonance, similar to Bourgeois and Neslodek, which is also highlighted in the bottom right. In the near future, this is a bit of work that's in preparation, but we need additional control experiments to solidify the carrier mechanism in our work. For acknowledgements, I would like to thank our funders, the National Science Foundation, the Department of Energy, and especially the CREST Ideals Center, which is now in phase 2. Professor Carlos Murillas, Dr. Kang Zhu, Dr. Daniela Pagliero, Dr. Gabriel Lopez Morales. This work would not be done without their expertise and feedback. And I'd also like to thank CREST Ideals Director, Maria Tamargo. Now, I'd also like to highlight that this work, I did a superficial summary of the photocurrent work. And what I would like you to do at APS is to visit the talk of Kang Zhu, which is on Wednesday, March 6, 2024, in room L100C. And Kang's talk is from 12:30 to 12:42, and he will be giving a more in-depth analysis of this work. I thank you very, very much for your time. Enjoy the conference. Thank you, APS, for allowing for this online platform, and enjoy the rest of your week. Thank you so much. Bye-bye.